Hello everyone, I'm Yuk Zhang from University of Southern California. Welcome to my talk entitled C2PI, an efficient crypto-clear two-party neural network private inference. In this talk, I will start from the background of private inference and then introduce our work, C2PI. Specifically, I will first introduce our hypothesis and the inference data privacy attack. Then, I will move on to the motivation and framework of C2PI, followed by the technical details. Afterwards, I will present our experimental results and summarize my talk. With the increasing complexity of deep neural network models and their incredible training cost, machine learning inference as a service has become an inevitable solution, saving significant time, cost, and effort in ML services. However, increasing privacy concerns challenge the inference procedure when a client and a server hold the private inference input and the private network separately and do not want to reveal their private properties to each other. To address this privacy issue, private inference has appeared. Private inference leverages multi-party computation protocols to protect client data from server and protect server model parameters from the client. Semi-honest threat model is a common threat model in private inference, where the two parties strictly follow the protocol but try to reveal their collaborators' private data by inspecting the information they received. Our work follows the semi-honest threat model. Delphi is a classic private inference method. Delphi contains an online phase and an offline phase, and moves most heavy procedures in MPC protocols to the offline phase. The linear operations are performed via online secret sharing and offline homomorphic encryption, while ReLUs are operated via garbled circuits. The drawback of private inference is its high computational and storage costs. Private inference presents more than 300 times latency and more than 3,000 times communication than regular inference. The nonlinear ReLU operation is the bottleneck due to the expensive corresponding MPC protocol. There are three methods to optimize existing private inference schemes. The first method is to identify and replace less important ReLUs with polynomial functions, which can be operated via less expensive MPC protocols. The second method is to optimize the MPC protocols for ReLU. The third method is to prune unimportant ReLUs. In existing private inference methods, server and client jointly compute each layer via MPC protocols. After performing one layer, both server and client will have a share of the layer output, and the summation of their shares equals the layer output. We propose to latent existing private inference methods from a new perspective by proposing a hypothesis that server cannot reveal client data, even if later layers are performed without MPC protocols. If this hypothesis is true, we can find a boundary layer and leverage MPC protocols before the boundary layer. That said, client can reveal its share to the server, and the server can independently perform the subsequent layers. We call the layers before and include the boundary as crypto layers, and we call the layers after the boundary as clear layers. Then the privacy concern becomes, can server recover client's private input from the boundary layer and clear layers outputs? We use inference data privacy attack to evaluate whether server can recover client's private input. There are three kinds of inference data privacy attack. The first one is maximum likelihood attack. In MLA, server recovers client's input from an intermediate layer output through gradient descent. This is doable because server has both model architecture and model parameters. The second inference data privacy attack is the inverse network attack, where server constructs a CNN inversion model M prime and trains it by taking the intermediate layer output as the inputs and the recovered inference input as output. After training the inversion model M star, server can recover client's input by conducting inference on M star. The third method is the enhanced inverse network attack, referred to as ENA, where M star is constructed with more powerful residue blocks instead of simple convolutional layers. To check our hypothesis, we applied MLA on VGG16 on CIFAR10. We used structural similarity to evaluate the recovered image, and an SSIM below 0.3 indicates a failure recovery. From our results, we can see that server cannot recover client's input from layer outputs after layer 10. So server could potentially be allowed to have layer outputs after layer 10 for a lighter PI procedure without violating the client's data privacy. Before talking about our framework, I would like to clarify the privacy goals of our work. Firstly, client can only learn server's network architecture of the crypto layers and the output of the inference. On the other hand, server can learn only outputs of the boundary and clear layers. Client's private input cannot be reviewed during operations of MPC protocols nor recovered by IDPs. Physical attacks such as side-channel attacks are out of the scope. This figure presents the framework of our C2PI. Firstly, server searches the boundary layer. I will illustrate our boundary searching algorithm in the next slide. Then, server and client jointly compute the crypto layers via MPC protocols. At the end of this step, both server and client have a share of the boundary layer's output, and the summation of their shares equals the boundary layer's output. Then, client adds some noise to its share and reviews the noiseless share to the server. Finally, server independently computes the clear layers and reviews the inference output to client. Please note that in semi-honest threat model, server will not lie on the boundary. Our boundary searching procedure contains two phases. In the first phase, server conducts IDPA backward until IDPA succeeds at layer L prime. The potential boundary is layer L prime plus 1 because this is the first layer that IDPA fails. Then, in phase 2, server adds noise to the output of layer L prime plus 1 and check the accuracy. If the accuracy is larger than the predetermined accuracy threshold, layer L prime plus 1 is returned as the boundary. If the accuracy is less than the accuracy threshold, server repeats this procedure forward on the subsequent layers until obtaining a satisfactory accuracy, and the corresponding layer will be returned as the boundary. In C2PI, users can configure the SSIM threshold for different privacy levels. It is clear that a more powerful IDPA leads to more robust boundary. Therefore, we propose a distillation-based IDPA referred to as DINA for our C2PI. Different from prior IDPAs, DINA takes advantage of the fact that server has access to the intermediate layer outputs and leverages the intermediate layer outputs to guide the training of the inversion model. Assuming DINA is performed at layer L prime, server partitions the target model before L prime into subblocks. DINA uses a basic inverse block, which contains a ResNet basic block and a dilated convolution layer to recover the input of one subblock. DINA selects the middle points between subblocks as distillation points. The equation here is the loss function of DINA, where the first term is the weighted sum of distance at distillation points, and the second term is the distance of recovered input and the original input. Our experimental results show that DINA outperforms both MLA and ENA by achieving higher SSIM on VGG16 on both CFAR10 and CFAR100. Now let's take a look at the effects of adding noise. Adding noise helps defend against DINA, as shown in our experimental results. Increasing the noise magnitude leads to lower SSIM of DINA. However, adding noise decreases the accuracy. As shown in the red figure, the accuracy drops with the increasing noise magnitude. Therefore, there is a trade-off between the resilience to DINA and accuracy. In our work, we use the noise magnitude of 0.1. Now we are ready to find the boundary for a model after plotting the accuracy with client-added noise and the DINA's results. For example, for AlexNet on CFAR10, we first identify that layer 4 is the earliest layer presenting an SSIM below 0.3. Then we check the accuracy of adding noise to the output of layer 4 and find that the accuracy drop is acceptable. So layer 4 is the final boundary for AlexNet on CFAR10. For AlexNet on CFAR100, we find that layer 3.5 is the earliest layer presenting an SSIM below 0.3. However, the corresponding accuracy drop is too large, so we check the subsequent layers until we get an acceptable accuracy drop at layer 5. And layer 5 is the boundary for AlexNet on CFAR100. Following the same procedure, we can find the boundary for VGG16 and VGG19 on CFAR10 and CFAR100, respectively. Here we present our experimental results on computational savings. We apply C2PI to the classic Delphi method and the state-of-the-art Cheetah method. When the crypto layers are performed with Delphi, C2PI achieves up to 3.88 times and 2.9 times speed up for VGG16 and VGG19, respectively. When the crypto layers are performed with Cheetah, C2PI is about 1.71 times and 1.82 times faster than full Cheetah for VGG16 and VGG19, respectively. To summarize our work, we propose an efficient two-party private inference framework, C2PI, which leverages IDPA-based privacy evaluation to relax existing private inference methods. We also propose a powerful distillation-based IDPA DINA that can recover higher quality images than its alternatives. In C2PI, DINA is used to find a rigid boundary that guarantees the proposed IDPA-based privacy. Moreover, users can set the privacy level by tuning DINA's failure threshold. Finally, C2PI protects the model architecture of clear layers while existing PI schemes review the model architecture completely. For broader impact, C2PI can be applied to any existing two-party private inference scheme over semi-honest threat model, and C2PI can be adapted to PI methods over malicious client threat model. Moreover, DINA helps address the privacy issue in other ML application situations, for example, split learning and split inference. Thanks for your attention. Please let us know if you have any questions.